Okay, this is going to be rather a short video here. We only have like one new idea, but I'm going to show you throughout this course you're going to be responsible for a number of functions, and here we're going to take a look at those if I haven't shown you this before. So what we have here, they're called the Toolkit functions in this textbook, and there are key functions that we need to know. Like, you need to know the basic shape of all of these. Now, as we're going through here, I guess what I can add, we may have seen this earlier. Now, this is the constant function. It means that you just y equals 3, y equals 4. It's going to get you a horizontal line. It doesn't change. Now, we're going to take a look. Remember how we did our increasing and decreasing. So if I were driving a car from left to right, I'm not going uphill or downhill anywhere. So it's not increasing or decreasing. Okay, an identity function is a line. That's all it is. So we'd have something where it equals x. We'd have a slope here. But so this is the basic one. And what we can do is transformations on this. We can move it up or down or tilt it. But this is the basic shape. Now, if you're driving your car from left to right, you see we're always going uphill. So if I were to put that in our interval notation that we were using, so as I'm driving from left to right, I'm going on all the x's, I'm going uphill. All right, now how about the quadratic function? This is the x squared. Now, it has the shape of a u. It's going to be a very important shape for this course. Now, where are we decreasing? I'm going to start with that one. As we're moving from left to right, we're going from negative infinity to 0. And now I have a local minima at the point 0, 0. Now, from 0 to infinity, I'm going uphill. So again, you are going to need to be responsible for these shapes. This is cubic. And if we said, well, where are we going uphill? We're going uphill forever. So we're always increasing. So that shape is what you're going to need. The color reciprocal function here gets this shape, and you're always decreasing. Notice how they put the union there. You never get to 0, so because it's got an asymptote there that we'll talk about later, it doesn't touch it. This is reciprocal squared. We're going uphill from negative infinity to 0, but we never quite get there, decreasing from 0 to infinity. All right, here's a weird looking one. This is the cube root function, and it's always increasing, so negative infinity to infinity. And then this is the square root function. I don't know if I've talked about this before, but do you notice when you take a square root, theoretically you get plus or minus 9 or 3 or whatever. Well, if you do that, it's not a function because it would actually have the same picture down at the bottom, and it would fail the vertical line test. It would not pass. So what we do in order to make sure that it can be a function is we limit it to the positive values. So this is the shape of the square root function. That's why we only have half a graph here. The bottom, if we were to be graphing the bottom, it would violate the function, so we stick with the positive values. So this is the basic shape. It's increasing from 0 to infinity. All right, here's another super important one, the absolute value function. It makes this v here, and we'd be decreasing from negative infinity to 0, increasing from 0 on. All right, now all of that is the shapes that you need, maybe a little bit of a refresher on what we talked about last time with local minimum, local maximum. Now the only thing we're going to add here is something called an absolute maxima. It's very simple. So before, any time we got to the top of a hill, we called it a local max, where the bottom of a hill was the local minimum. Well, an absolute maxima just means that it is the highest point or one of the highest points, and an absolute minimum means it's the absolute lowest point. So here's what I mean. If I were to go through here, I have tops of the hill at negative 2, 16, bottom of the hill at 0, 0, top of the hill at 2, 16. But look, we have some new points added in as well, these endpoints. So I want to find the absolute maxima, the absolute highest point on this graph. So not just local ones, what is the highest and lowest point? Well, the maxima, actually there's two because there's a tie. Negative 216 is the highest point on the graph as well as 216. Do you see? The highest point, the absolute maxima on this graph are these 2 points because they're tied. And the min, the absolute min, the absolute lowest point on this graph. This is clever. It's not this point at this valley. It's actually over here, which I think is supposed to be negative 10, or I'm sorry, is supposed to be 3, negative 10. So one more time. An absolute max is the absolute highest place on the graph. Well, that would be here and here because they're tied. The absolute minima would be down here. It didn't turn, it could have been this valley, but it turned out there's a point even lower than that because our graph ends here. Okay, I know that's not very much. I'm trying to think if there's anything I would add there. Yeah, I guess the only other thing I would say here is suppose we had it like we had last time. I'm going to draw this same kind of graph. But suppose it didn't have those endpoints. Then let's go through it again. Where would our absolute maxima be? These tops of the hills are the absolute maxima. They would be absolutes again, the highest points. But our lowest point, our absolute minima, there actually isn't one. Because the graph is always increasing here, we'd actually can be going on to infinity. There is no absolutely lowest point on this graph because it doesn't end like this one did. Do you see what I mean? Because it's going from infinity to infinity, negative infinity to infinity. This one never has an absolute low point because it never reaches one. So the best we could do is say the point 0, 0 is a local minima. So do you see the difference? Because this is so quick, I'm going to say it one more time. This graph, because it ends, has an absolute high points and the absolute low point down here. But one that goes on to infinity like this anyway, it has absolute high points, but it doesn't have an absolute low point. The best we can do there is a local minimum. It's not an absolute. Okay, I know there's not a lot there. Just remember you're responsible for those basic shapes. And we talked about the previous time increasing and decreasing. And now here we've added the idea. We had local minimum or local maximum. To this one we just added that there can be an absolute maximum and an absolute minimum. The absolute highest point and the absolute lowest point.